All right, so now that we've gotten our deriving out of the way, let's get to the fun stuff. Let's actually take some derivatives. And we're going to start with the derivative of tangent x. That's kind of the other core trigonometric function. And you might be going, well, you didn't give us that one yet. You only talked about sine and cosine. And I'm going to say, I know, and that's okay, because since tangent is sine and cosine, it's sine x over cosine x. So what I'd like you to do right now is pause this video and see if you can't use the quotient rule to get the derivative for tangent. Well, you should have started like this. Low d high d low over low squared. We get cosine x times cosine x minus sine x times negative sine x all over cosine squared x. And what do we have? Well, we have cosine squared x plus sine squared x over cosine squared x. And that numerator is just 1. And a simpler way to write cosine squared x would be secant squared x. So the derivative of tangent is equal to the secant of x quantity squared. Now, if f of x is sine of x times cosine x, what's this equal to? Give it a try. Pause the video. Use the product rule. See what you end up with. Well, if we use the product rule, we get first times derivative of second plus second times derivative of first. And we get cosine squared x minus sine squared x. But you know, one of the beauties of mathematics is oftentimes there's more than one way to go. And this original function is actually it sort of looks like the identity for sine 2x, but it's missing the 2 in front. So sine x cosine x is 1/2 sine 2x. Let's differentiate that. Well, that's easier. We don't have to use a product rule. We use the chain rule. So 1/2 times cosine 2x times the derivative of what's inside, which is 2. So our derivative is cosine 2x. And if you check your identities, well, you'll see that this is one of our trigonometric identities. So oftentimes there's a lot of different ways or multiple ways to differentiate a function, and the methods that you're going to use are going to differ depending on what you notice in a problem. Next example, secant x. Well, if you can't see how to do this derivative, that's okay, I'll help you. That's why we call it the secant. I'm funny. But anyway, secant x is 1 over cosine x, right? And that could be written as cosine of x raised to the negative first power. Now, derivative's easy. It's a power rule and chain rule. We bring the exponent down, decrease it by 1, and then multiply by the derivative of what's inside. And what we have then is sine x over cosine squared x, which could also be written as the secant of x times the tangent of x. And I write it this way on purpose for reasons that we'll see later on down the road. And there's no reason we just have to deal with trig functions. Let's throw an x squared in there. X squared times a trig function. Well, product rule, guys. You can do this. Pause the video, try and find this derivative. So we have x squared times cosine 2x times 2. We need a little chain rule in there. plus second sine 2x times 2x. And cleaning this up just a titch, 2x squared cosine 2x plus 2x times sine 2x. A lot of times we write it's just common convention to write the things that aren't in the trig function before the trig function instead of after. Not a huge deal though. Next example. Give this one a try. Let's see what you come up with. All right, so dy dx is equal to, it's another product rule. So what was the derivative of tangent? It was secant squared. And don't forget the chain rule. So that's first times derivative of second plus second times derivative of first. Derivative of natural log was 1 over times the derivative of what's inside, which would be 2x. And just a little cleaning, not a lot. 1/2 natural log x squared plus 1 secant squared x over 2 plus 2x over x squared plus 1 tan x over 2. And there we go. It's big, it looks messy, but this is the derivative. There's not really anything else that we can do beyond this point. Now let's start asking the kinds of questions that we saw back with the other derivatives. Find the gradient of this curve that has a trig function in it at a specific point. Because remember, calculus helps us find the rate of change of a curve at specific places on that curve. So, we need the derivative. Pause it, find it please. You should get 3x times negative sine 2x times 2 plus cosine 2x times 3. And now we want to evaluate that derivative at the x-coordinate of 5 pi over 6. So we have negative 6 times x sine 2 times x plus 3 cosine 2 times x. And the x that I'm putting in, of course, is 5 pi over 6. So, what do we have? Well, we've got negative 5 pi, and this is going to be sine of 5 pi over 3. Sine 5 pi over 3 is negative square root 3 over 2. Plus 3 times the cosine of 5 pi over 3, which is 1/2. So, the gradient of this curve at x equals 5 pi over 6 is exactly 5 pi times the square root of 3 over 2 plus 3/2. So all of the same stuff that we did earlier, finding gradients, finding tangent lines, finding normal lines, we can do that now with anything that has trigonometry in it too. And before I leave you with this video, there's one more example, and I want you to give it a try. Find the derivative of this. And, okay, so you should have tried, you might have got to the answer, you might not have, and it depends on the direction that you go, really, in how hard you have to work. If you use the product rule, cool, great. You worked really, really hard though, because I can expand this instead. Even if you expand it, you're going to have to work really, really hard to get the derivative. But if you notice, the two things in parentheses are just trigonometric identities. They're both versions of Pythagorean identities. 1 plus tangent squared is secant squared. And 1 minus sine squared is cosine squared. So this isn't the derivative. This is still f of x. And I can simplify f of x a little bit more. Well, secant x times cosine x is just 1. So this original function, through simplifying, I find out is equal to 1. Well, that's ridiculously easy. The derivative of a constant is just 0. So my question for you is, how hard did you work to find this derivative?